Every American schoolchild is taught that Alexander Graham Bell invented the telephone. We are shown pictures of a distinguished, bearded gentleman sitting in a Victorian laboratory, spilling battery acid on his trousers, and shouting into a brass cone to his assistant, "Mr. Watson, come here. I want to see you." It is presented as one of the ultimate triumph stories of American ingenuity. A brilliant inventor working late into the night, striking lightning in a bottle, and magically creating the device that connected the world. There is only one problem with that story. Almost every single part of it misses the real breakthrough. Alexander Graham Bell was not the only person trying to build a telephone in the 1870s. In fact, he was locked in a ruthless, frantic race against some of the greatest electrical minds of the 19th century. Men like Elisha Gray, Thomas Edison, and Western Union engineers, brilliant inventors with vastly more funding, better equipment, and decades of experience in electrical engineering. They all saw the exact same goal. They all had access to the exact same copper wire, the exact same batteries, and the exact same telegraph lines stretching across the United States. Yet all of those electrical geniuses failed to build the telephone first. Why? Because they were all looking at the problem through the lens of electrical engineering. Alexander Graham Bell was the only person who looked at it through something entirely different. While everyone else was trying to figure out how to make electricity carry a message, Bell saw something no one else missed. He understood how the human ear actually hears. To understand what Bell saw, you first have to understand the massive technological wall the world had hit by the 1870s. The world was already connected by the telegraph. It was the Victorian Internet. Thin copper wires stretched across continents and beneath oceans, carrying pulses of electricity that represented dots and dashes, Morse code. It was revolutionary, but it had a catastrophic bottleneck. A single telegraph wire could only send one message at a time. As global trade exploded, the wires were jammed. Railroads, stock markets, and governments were desperate for a way to squeeze more data through a single piece of copper. The highest stakes technology race in the world at that moment was the creation of the harmonic telegraph, a machine that could send multiple Morse code messages simultaneously over the same wire by using different musical pitches. If you could send 4, 8, or 12 telegraph messages at once on one wire, you would instantly become a multi-millionaire and control the flow of global communication. Elisha Gray, a master electrician and co-founder of Western Union's primary supplier, was working on this exact problem. Thomas Edison was working on it too. They were elite electricians, thinking purely in terms of electrical circuits, switches, and currents. And so was Alexander Graham Bell. Born in Scotland and relocating to Boston, Bell was also trying to build a harmonic telegraph. But Bell had a background that none of his competitors possessed. He was not an electrician. He was a speech therapist. Both his mother and his wife were deaf. His father had invented visible speech, a system of visual symbols designed to help deaf people learn to speak by showing how the mouth, tongue, and throat shaped sound. Bell spent his days studying the mechanics of human speech and the biological structure of the human ear. To Bell, sound was not a mystery. It was a physical, mechanical wave moving through the air. While Edison and Gray were looking at a wire and thinking, "How do I send more electrical pulses?" Bell was looking at the same wire and thinking, "How does a human voice vibrate the air?" The breakthrough came from an incredible, almost grotesque experiment. To better understand how the human ear processes sound, Bell obtained an actual, preserved human ear from a medical university. He mounted this biological ear onto a wooden apparatus. He attached a tiny straw to the ear's delicate internal bones, the stapes, incus, and malleus, and rested the straw against a piece of glass covered in soot. When Bell spoke loudly into the dead human ear, the sound waves vibrated the eardrum. The eardrum moved the tiny bones. The tiny bones moved the straw. And the straw traced a continuous, smooth, wavy line through the soot on the glass. It was a profound, life-changing revelation. Bell stared at those smooth, undulating lines in the soot and realized what every electrician in the world had missed. Telegraphs worked using a break-and-make circuit. The key was pressed down, the circuit closed, and a sudden surge of electricity shot through the wire. The key was released, the circuit opened, and the electricity stopped dead. It was binary, on or off. Sound was represented by sharp, jagged bursts of current. Every other inventor was trying to send speech by breaking the electric current into tiny, rapid, jagged pulses, trying to turn sound into a series of microscopic clicks. Looking at the trace marks from the human ear, Bell realized that human speech is not binary. It is not on or off. It does not move in jagged clicks. Human speech is a continuous, complex, undulating wave. The voice never truly stops moving air. It gently rises, falls, bends, and flows. If you try to send speech using a telegraph's on and off current, you get nothing but static, harsh pops and unintelligible noise. Bell realized that if he wanted a wire to carry the human voice, he couldn't use a circuit that turned on and off. He had to create a continuous, unbroken electrical current that fluctuated in exact harmony with the sound wave hitting it. The electricity itself had to become a physical shadow of the sound wave. In the summer of 1875, Bell and his assistant, Thomas Watson, were experimenting with their harmonic telegraph in a hot Boston attic. Watson accidentally plucked a steel reed on his end of the apparatus. Usually this would just open or close a circuit. But this time, the reed was stuck against a magnet. When Watson plucked it, the vibrating steel induced a tiny, continuous, undulating wave of electricity in the wire, without breaking the circuit. In the next room, Bell heard a faint twang coming from his receiver. It wasn't a sharp telegraph click, it was a musical tone. It had timbre, it had resonance. It had the smooth, wave-like quality of a physical sound. Bell rushed into the room. He realized that the tiny continuous current induced by that vibrating reed had reproduced the exact physical motion of Watson's pluck across the wire. While Elisha Gray and Thomas Edison were still trying to perfect multi-channel Morse code by chopping electricity into finer pieces, Bell completely abandoned the harmonic telegraph. He realized that if a wire could carry the continuous vibration of a steel reed, it could carry the continuous vibration of a human voice. On March 10, 1876, Bell perfected his liquid transmitter. When he spoke into the membrane, his voice pushed down on a small rod sitting in an acid solution. As the voice vibrated the rod, it smoothly altered the electrical resistance in the liquid, creating a continuous, unbroken wave of electricity that matched his speech perfectly. Miles away, that exact same wave vibrated an iron diaphragm, pushing the air and replicating his voice into Thomas Watson's ear. "Mr. Watson, come here. I want to see you." When Bell submitted his patent, Elisha Gray submitted a caveat for a similar idea on the very same day. It turned into one of the most famous legal battles in American history. Western Union bought Gray's and Edison's concepts and backed them with millions of dollars, attempting to crush Bell's young company. They argued that Bell's device was weak, crude, and barely functional compared to their massive telegraph infrastructure. But Western Union lost. They lost because Edison and Gray had built better electrical equipment, but Bell had grasped the fundamental physics of sound and human biology. They had built machines for telegraph operators. Bell had built a machine for human beings. Within a decade, millions of miles of wire stretched across North America, not carrying cold, robotic clicks of code, but the warm, continuous, undulating waves of human emotion. Consider what would not exist if Alexander Graham Bell hadn't looked at a biological human ear in a Boston laboratory. Without Bell's realization that continuous electrical waves could mirror physical phenomena, the entire foundation of analog technology would have been delayed for decades. The phonograph, which Edison only realized was possible after seeing Bell's continuous wave concept, relied on the exact same continuous acoustic groove. Radio broadcasting, television signals, early audio recording, and the entire 20th century telecommunications grid were all built on the single principle Bell discovered: converting physical sound into continuous electrical waves and back again. Even modern digital audio, which eventually converted sound back into binary numbers, relies on sampling Bell's continuous wave hundreds of thousands of times per second to fool the human ear into hearing a smooth sound. So, what did we actually miss about the story of Alexander Graham Bell? We missed the fact that the greatest technological leap in communications history was not made by an electrician. It was made by a man who studied deaf ears, who understood that human speech is a continuous wave of moving air, and who realized that electricity didn't need to click. It needed to flow, like a voice. Every other inventor was trying to teach human beings how to talk to machines. Alexander Graham Bell was the only one who taught electricity how to talk like a human.